All right, so welcome back to the second portion of this class. Today I'm going to start the discussion about dimensionality reduction and more specifically on principal components analysis, or PCA for short. PCA is one of the most important dimensionality reduction technique. In fact, it's an unsupervised learning method in the sense that we do not need to know much about the data set apart from the features or the variables that we talked about last time. It is a linear dimensionality reduction technique, and the primary goal of this method is to essentially represent high dimensional data using only fewer dimensions. And the whole idea is that we would like to preserve as much information as possible. So here, when I say information, I really mean the variance levels in your features. So in other words, PCA will look for the directions in the data along which the data varies the most, and then you can re-express this data set using those directions. So, for example, in this particular slide, you could see that the first principal component, PC1, has the highest levels of variance, as you could see, because the data, if you just draw here a line horizontally from where the very first data point starts with and the very last data point finishes with here on the rightmost scatter over here, you'll see that it has a longer stretch if you compare that with the PC2 here with lower variance. In fact, the first principal component vector will always be the vector with the highest variance where the data is going to be projected. So now let's move on to talk a little bit more about what's the motivation behind PCA. Why does it exist in the first place? Most of the modern data sets are often either high dimensional or noisy or sometimes even redundant. We have some features which are capturing the same information in your data set. And another thing, and of course, when I say no, high dimensional, I also mean computationally expensive to process, right? If you would like to train a classifier or or a clustering algorithm, it will take way more when your data set is long or big at the horizontal level and having a lot of features. So many features are correlated, meaning that they carry overlapping informations. And so principal components analysis was developed to address this problem, and really answer to the question of how can we remove redundancy while also keeping the most essentials information in the data. So here you could see a two-dimensional data set with two attributes, as I mentioned. So attribute one and attribute two. Um, and so the new axes are called principal components. And they are also known for better explaining the structure of the data. So the second principal component is usually and always going to be orthogonal to the PC1. So as I mentioned, PC1 will always be the principal component with that if we use it, we'll have the highest variance. If you project your data on PC1, you will have the highest variance. The second one is by default the orthogonal vector on PC1 that we have here, and it carries the remaining variance in the data. So each principal component contributes with some amount of information, and that contribution itself is quantified using the eigenvalues. So eigenvalues is the second important concept that we're going to talk about today here. So in the right hand side over here in this plot here, you could see the different eigenvalues which are coupling each principal component. So the first principal component will always going to carry the highest eigenvalue, which is around 2.5 over here. The second principal component is having an eigenvalue of 1.5, and it's going lower and lower until the eigenvalues are almost stagnant or converging towards a very small value, which means that principal component number 6 is probably not going to add up much to all the other principal components, because we can say that this is how much information it contributes to, which is very small in this case. All right, so the next question, so how many components are should we use for expressing our data set is a question that we're going to ask, and we're going to answer in the remaining slides, before trying to understand how does it work in the first place. So the way it works is that first, PCA is trying to minimize the sum of the squared projection errors. And what I mean by sum of squared projection errors, if you could see on the left-hand side here, you see data is reduced from 2D, right, which we have here x1 and x2 in the original feature space. So in theory, we should have only two columns, x1 and x2, and every single dot here or X here scatter represents one tuple or one object from our data set, which are the rows of our feature space. Now, in our original space, these are the X1 and X2 projections for every single tuple. On the red line that you see here, this is our first principal component and the only one that we use to represent or to minimize the features of our data set. So you could see here that if you project every single dot here into this line, you'll see that, well, we are getting a high, a lot of variance levels over here. So if you just look at the very beginning of this line with the end of this line, we could see that it crosses quite a long a long amount of in the X segment over here, but also we could notice that there is a small relative projection error, which is this blue line over here. If you just do the projection of every single X into the red line, you'll see that, well, it's almost on top of the red line. It's not quite there yet, but in approximation, right? If you just project it in the red line, this is what we're losing a little bit of information over here, which is in the blue segment over here. So this is known as a projection error. So typically, we would like to minimize it as much as possible when we produce our our new PCA projections. Uh, on the right hand side, you could see the same exact example, but here we're just projecting from 3D, right? So x1, x2, and x3, or three dimensions, into 2D or into a hyperplane, in this case, of U1 and U2. So you might notice that I'm using U1 as U in order to describe the principal component, and I'm also using Z as the new projection, or as the new vector, which describes our reduced data set. So if you look at the initial domains, we moved from R2 to R, right? From 2D into 1D in the first example, and then from R3, which is three dimensions, into R2 in the second example, by projecting all those blue scatters into all these two-dimensional hyperplane over here. So our Z has only two dimensions, Z1 into and Z2 in this case. All right, so now let's talk about how can we produce our PCAs. So the very first step, which is a mandatory step, before applying PCA, we must do some pre-processing. So it is very critical. So we must first ensure that all the features are what is known as mean normalized. And this is especially important in case we have attributes that have different units or magnitudes. So without normalization or standardization, the PCA might incorrectly prioritize the features which are naturally larger in terms of their numeric ranges. For example, if one of the features in our data set or one of the columns represent the house size, and the second feature is the number of bedrooms, then if you don't normalize your data, then PCA will naturally give way more importance to the house size, which is few units higher than the number of bedroom here. So the very first step that we do is, of course, for every single features, right? So if you have a training set x1, x2, and xm, For every single feature that we have, we find the mean of that particular column, which is also represented as a mu sub j, which is the feature j in this case, and we take the average of all the values of that particular column, which is described as j in this case. So for every single value, what we're going to do is that we're going to take the value of that feature, xj in that particular column, we subtract the mean of that column from it, and we divide by the standard deviation of that particular column. And that way we're getting a new value, right? Which is a better representation and scaled value of that particular tuple of that dimension here. So in other words, if I were just to describe this in terms of our feature space that we had earlier, our x's are the tuples, right? Which is here x1, x2, all the way to xm, or which are my object in this case. The J's are essentially describing the columns over here. So J1 all the way to Jn in this case. So for every single tuple object that we have here, we apply what's the mean per column, what is the standard deviation per column, and for every single value I replace that with the new value, which is the standardized value over here, which is the old value minus the mean of that column over the standard deviation of that particular column. So that way we're getting a mean normalized data set where all the features are having the same range of values between -3 and 3 in general over here. All right. So now that we have our the data set which is normalized, we need to apply what is known as the covariance matrix, and to find the covariance matrix of our in our data set. So, so the covariance matrix essentially is a 2D matrix, and it tells us what's the variance between variables. So variance by definition tells us how much a single feature spreads out, right? We already saw that before. And now covariance tells us how two features changes together. And so if you could see here, the sigma here is our covariance matrix, and it's nothing but xi, which is every single tuple that we have, and we take the outer product with the same xi transpose. So this will measure how every pair of features co-varies for one data point, and then it averages that across the whole data set. A point, and it gives us some covariance structure of the entire data. So you could see 1 over m is our averaging factor over here. So once we have our sigma, we're going to see later that we would like to probably try to decompose that using the SVD or single value decomposition in order to get some really nice matrix that we're going to use later. So essentially, if you decompose sigma, we don't have to learn about SVD. We just need to know that SVD is the matrix decomposition method, which gives us three important matrices: U, S, and V. You might want to forget about V because it's not very important for us. But U is my covariant my eigenvector matrix, and S is my eigenvalue matrix. So essentially, the columns of the U are the eigenvectors, which are shown in the previous slides here in orange, PC1. The second column of U is PC2. The third column of U will be PC3, etc. And now the S, which is the middle matrix that is being decomposed from sigma, will give us the values. So the diagonal the values of S will give us what are the corresponding eigenvalues for every single principal component. So essentially, the values in this case will be 2.5. The second value will be 1.5 along the diagonal of the S decomposed matrix that we have over here. All right, so this plot shows how different covariance structures affect the orientation of the principal components. So you could clearly see by look that the eigenvector points, you can guess what's the eigenvector from the plot, which is the direction with the highest variance of x, of the x and y scatters in this case. So the eigenvector points in the direction where the data varies the most, and visually, PCA will always going to find the best fitting line or plane through this particular data scatters, right? So let's try to interpret what is this sigma over here telling us about our data set for this two dimensional scatters in this case. So you'll start with the very first variable over here, which is the variance, right? So this is going to be the variance of x, the variance of x independently of y, right? So variance of x independently of y is what my sigma or my covariance matrix we're going to capture. Now the second one is the variance of y independent of x. If you just see what's the variance value of y, of my y component regardless of x, then it should be around 3. So this clearly tells me that, well, the variance of y in this case is higher than the variance of x. If you look at the diagonal values of your covariance matrix here, this tells us what's the correlation factor between x and y, right? Which is also known as a covariance a factor, right? So in this case, we could see that, well, it's 0.4. It is not null. It has some strength, which is almost 0.5, which means that, well, probably these two variables are correlated, and they are positively correlated because they move along on the same direction, meaning that when x is higher, then there is a tendency that y is higher as well. So that's how the two variables are moving together in this case. So they are correlated in some way. Well, the same thing can be thought of in the third example over here. You could see that, well, since there is no linear correlation and there is no positive trend going on, nor any negative trend going on, they are just kind of correlated, but only at the horizontal level over here, their covariance factor is equal to 0 in this case. So we can say that, well, they're not really correlated because there is no linear correlation at any positive nor negative trend in this case. Well, the same thing can be thought of here. We can clearly see that the variance level of x, right? So if you just plot here, what's the interval in which the values are ranging in the x variable, you could see that, well, we can say that they are about 6. That's how we quantify their variance in the x axis. If you do the same thing in the y level and see how much room do they use in order to move along the y directions, it's almost half of that of the x direction. In fact, it's only 3. So the variance level in the y-axis is only 3 in this case, which tells me that probably x is a good variable compared to y, and this is directly encoded in my sigma or my covariance matrix, which tells me that this is quite a powerful matrix here. It tells me not only how powerful are those variables, but also how they are correlated in between each other. So if you look at the last example over here, you could see that, well, there is some kind of negative trend going on, and therefore we have a minus 0.4 as being the covariance factor between x and y, which tells me that they are linearly moving to opposite sides, right? So when the y value is higher, the x value has a tendency to be low, and vice versa. When x is high, then x is high, which is the highest component over here, then usually the y is low in this case. The same thing can be thought of along the variance levels over here. So if you look at the variance of y, right? So the variance on the y-axis is equal to 2, while the variance in the x-axis is equal to 3. And you can clearly see that x is moving along a wider interval compared to the y-axis, where it moves only on a smaller interval of 2 in this case. Um, this and you can extrapolate in the last example by yourself. So 0 is our covariance factor over here. Well, because we don't have any trend going on between x and y. There is a high variance of y. You could clearly see that. Well, we're moving in a very long segment of magnitudes in the y-axis compared to the x-axis, which merely moves in this small portion here, which is quantified as being having a variance of 3 only. So 7 versus 3 in this case. So this is exactly how would you interpret your covariance matrix in general, and how is that useful. So before trying to use it for PCA, this is how would you understand it first, before moving further in the next portions of the PCA steps and extrapolations. All right, so moving on to the next slide over here. So the eigenvector can be clearly guessed, as I mentioned earlier in this case. So the one which gives us the highest variance, right? There are many lines that I can draw just for fun here that could be a possible PCA, right? So it could this PCA, or this one could be a PCA. This one could be a PCA as well, right? Or principal component as well. However, the first principal component is the one that if that will span the maximum when projected along that axis, meaning that if I look at how much span the first point and the last point is in terms of values, you'll find that I will have the highest segment, the most that has the most length, right? So if I do that with this, let's say this axe over here, I'll say that this axe will span only in this point around this value over here of magnitude and this value over here. So this segment is way smaller compared to the orange segments that I just drew in the beginning of the slide. So the principal component will always be the line with the highest variance, and therefore spanning the most values, magnitude values along that axis. Okay, so a PCA algorithm summary. Let's just try to recap of all the concepts that I discussed so far. So the very first step of the PCA, of course, is going to be the mean normalization. So after a mean normalization, which is very optimal feature scaling, and this is making sure that all the features has the same importance, right? So no feature will going to be naturally naturally having higher magnitude values and therefore treated with more importance with PCA, and that's what we're making sure in the very first step. So the second step is going to be, we need to compute our sigma or our covariance matrix for our data set. How we do so is simply by finding the outer product of x with xi transpose in this case, and you take the mean, which is 1 over m, 1 over all the tuples or all the objects that we have in this case. So once we have our sigma, we can apply a matrix decomposition method, like single value decomposition. There are other methods that I did not mention, but they do exactly the same thing. They are a little bit less or more slower than SVD, like an eigen decomposition, if you might have heard that in calculus class. But SVD in general, other methods will give you some very precious matrices. The only one that you should care of is U and S. So U will tell us what are the eigenvectors. So the eigenvectors will be the columns of that particular matrix, and S in this case will give us what are the corresponding eigenvalues for every single principal component. So the S matrix will be sparse everywhere, and it will have values only along the diagonal. So if you wish, the S here that I am showing you in the slide will have zeros everywhere, right? But in the diagonal of this matrix, I will have my eigenvalues, eigen 1, eigen 2, eigen 3, etc., all the way to eigen n over here, which is my last principal component. All the other values that are along in this triangle will be equal to 0. So that's what the my eigen my eigen value matrix S will give us as a result in this case. All right, so now once we have that, the reduced data set, or U reduce, that I also that I also described as being the Z in the previous slide, will be nothing but the only K components, right? So because I want only a few components from from my U matrix, right? So I want, let's say, three principal components or two principal components in order to express the whole data set, because two principal components will allow me, let's say, uh, have the data or draw the data in 2D. Same thing for three principal components. We're going to see how can we choose K, which is how many components in the next slides. But the idea here is that once we have our U reduce, once we know how many components we would like to use, then we can find what is the Z, which is the coordinates of my new data set, which is nothing but the U reduce times X, right? So if you just take X, which is my original tuple, and times that U reduce, which is the principal components, only the first K of them, then I'll get the Z, which is my new data set. In other terms, if I were just to go back a few slides over here, my Z's are nothing but those dots over here in 1D, right? So what is the value of this X in this axis, or this axis here, which is my first principal component? Okay, uh, now the next question that I will ask is, well, now that I have my Z, I can easily find what is the reconstruction error, right? So the reconstruction error is telling me how much information did I lose in the process of finding my PCA. And the way it works is that we can easily map the reduced data back to the original space using the retrained principal component. Of course, the reconstruction is going to be approximate, but it preserves as much variance as possible given the K components. So in other terms, the Z that I just found, which is the U reduce, the U only using K principal component times X, will give me the new data set in a lower dimensional space. In this case, it's 1D. Now, if I want to know how much information did I lose and what is my approximate X in this case, all what I need to do is to take the U reduce times Z, which is this Z that I just found in the very first step. So an X, in this case, we will get an X approximation of in the original space of Rn, right? So if you compare the X approximation with the original X in Rn, that tells me, well, this is how much information did I lose, and this is the error, the error when mapping it into the PCA space, which is the low dimensional space in this case. Of course, if you look here at the dimensions, so X approximation will be in N, right? So we have N features. So of course, the approximation of X will be in N. The U reduce will be N times K. K is the number of component that we used. And Z is in K dimension, because I used, in this case, K is equal to 1 in this particular example, but it could be K is equal to 2 in case I use 2D or 3D PCA for that matter. Okay, now we're going to answer one of the most important questions about PCA, which is, how do we choose K? How do we choose the number of components? Now, if I just ask someone from class and say, hey, what's your favorite K? Maybe someone might tell me that I like K is equal to 2 or K is equal to 3. You might have your own motivation, and the motivation could be that, well, because I would like to visualize the data in 2D or 3D. Right, that's great. But now what if you would like to reduce the amount of data just for the sake of dimensionality reduction, not necessarily for visualization? Maybe you would like to have less amount of features for training a model and having a quick and dirty classifier trained on let's say 5 or 10 features. How do we choose K in that case? The good news is that we have a very nice and systematic way to find the K, and that's will always going to be depending on how much variance, how much information you would like to keep in your data, right? So we're always going to measure the total variance in the data in terms of this nice this nice ratio that we have in the slides. So if you look closely in the slides over here, we are computing two things. We are computing what is the x, original x, minus the x approximation, which is the one that I showed in the previous slide when you time the u reduce with the z, right? So this is kind of like the error, the projection error, and squared, right? And we compare that with the denominator, and the denominator in this case is nothing but the x. In other terms, how much is the error in terms of the original data, right? So how much the percentage of that particular error is with respect to the original data magnitude, which is in x magnitude original in the original space in this case. So I might choose to say that I would like to keep about 99% of the variance, which is kind of or 95% of the variance. Or if I would like to be even less conservative, I could choose only 90% of the variance. I'm okay as long as 90% of the information is being conserved in this case, and that way I can allow up to 10% of error with respect to the original data in this case. Now, if typically I see very often that 95% variance is being an acceptable threshold for choosing the number of components. Now, the way it works is that I start first, and this is a small pseudocode about how to choose the K with PCA. So after, of course, finding the x approximation using the u reduce and the z's in the reduced space in this case, we need to start checking for we're starting with k is equal to 1, which is the lowest possible number of principal components that we can use. So for k is equal to 1, I compute this ratio that I have over here. And then I ask myself, is this less than 1%? Because I would like to conserve 99% of variance in this case. If it's the case, then well, you're done. Good news, you're done. With only one principal component, you were able to keep 99% of the information in your data. If it's not the case, which is probably going to be so, because one principal component is quite a small number of vectors to project into for a very large data set, then we keep going. We increment k, and we just increase the number of components with k is equal to 2. All right, now we do the same thing with x in 2D, uh, and after reapproximating x in the original space using the z's and the u reduce, can I now achieve 99% of information being kept? If it's the case, then I am done, and I use k is equal to 2, right? So it's always going to be a question of variance and information loss that I would like that I can that I can afford to lose at the end of the process. Okay, now there is a small tweak, or I like to call it a shortcut, right? So here, using this ratio, I might be able to find the number of k, but yeah, I still need to compute through the x approximation, right? Which necessitate the computation of the z's, and then and then I need to time it with the u reduce and still compute this ratio over here, which is some extra work from my end. Now, there is a nice shortcut, which is the right-hand side of this slide over here. If I am bothered by computing this ratio over here, there is a nice approximation or a proxy to this ratio over here. And the proxy, the proxy is nothing but 1 minus taking S, which is the eigenvalues from the eigen value matrix over here. If I take the first S over the sum of all the S's, or the eigen values that I have along this the diagonal of my eigenvalue matrix over here, it's an approximation of this particular error ratio in order to quantify how much variance is kept in my data set. Now, with S, I can take a subset. K is equal to 1, and I start with K is equal to 1. If it's less than 1%, then I increase and I take the second S, which is the second value over here of the diagonal of my S matrix, and I add that in the nominator part of this particular formula, and I compare that with the sum of all S's, 1 minus this particular measure over here. If it's less than 1%, then that's good news. I should stop at K is equal to 2 in this case. If it's not, then I do the same thing as the previous step, and I increase K with K is equal to 3 in this case. Okay, that's great. So now, just to recap, in this particular slide over here, now that we understood how to compute my PCA, which is the summary slide over here, by first normalizing the data, then decomposing then finding my sigma matrix, decomposing my sigma matrix, taking the U and the S's and the S. So the U will allow me to take the first K principal components and time it with my X in the original space in order to get the Z coordinates of my data set in this new reduced space of 2D, 3D, or 4D, whatever K is chosen in this case. Now that I know how to compute my PCA, the next step is to find what is the number of K, or the number of columns that I need to choose from my U matrix after applying the SVD. The first way is to compute this ratio, right? Which is X minus X approximation over the sum of all X's. This is great, but we have the extra step of computing X approx using the U reduce and Z. Now, a shortcut of that is just to grab my S, which I already have computed, and compute the ratio of the sum of the eigenvalues of the first S's and over the denominator part of the sum of all the S's from the diagonal of my eigenvalue matrix in this case. Okay, so why do we do this all over? So PCA is often used to speed up the supervised learning process. We apply PCA only on the training set. It's very important to note that you should never use PCA in the test set in your data set. And the reason we use it is for reducing the training time. If you're applying any classifier on the new data on the new reduced data set, then it can improve numerical stability. And PCA should never be used on the test data. So this is just an example of a speed up. So let's say that I have a data set of M tuples or M objects. So X1, X2, Xm is my objects or my rows, and Y is their corresponding classes, right? So in this case, we have images of 100 by 100 the pixels, right? So which tells me that our data set is in the 10,000 dimensional space. Since PCA is an unsupervised learning process, I just need to feed it the X's. I don't have to tell the algorithm about the Y, which is my labels or the class of those images, which could be like the Y could be just a representation of, well, this is a dog, or this is a cat, or this is another object that is embodied inside of the image. So the unlabeled data set is being passed to the PCA. The PCA, of course, after applying all the steps that we talked about, we're getting our Z's, which is our new coordinates in the lower dimensional space. Well, in this case, K is equal to 1000 according to this example over here, because R is to the 1000 in this case. Now, the new training set could be Z with the paired with the class of the first image, Z2 with the second image, etc., all the way to ZM paired with YM in that particular case. This is some examples of real trained models on the original space without PCA and with PCA as well. And you could see what's the impact of PCA on the training and the testing losses. So in this case, the lower the loss, the better. And just going also to discuss the accuracies, which is written in the title of the sub figures in this case. So without PCA, my accuracy was about 86.72 percent. Um, with PCA of 99%, which means that I'm using the variance level of 99%, I'm allowing only 1% of reconstruction error here, and that will lead a feature the number of features to be reduced from 780 to 526. My accuracy did not really budge that much. If you look at the accuracy, it's only 86.49, which means that, well, I did not really lose much in this case. And you could see also the losses is almost the same shape, the same conversions as the epochs are progressing in this case. You might look at the y-axis and you could see that, well, it's slightly different in terms of in terms of intervals. So therefore, you cannot compare them side by side, but you could see that, well, we're talking about the same, almost same accuracy. With the PCF 95% variance, the accuracy is still 86. So we're really not losing much. But look at the features. The features have been halved almost from the beginning, right? So it's only 256 features compared to 526 when we use 99% PCA, and it's way it's way less than half of the original features without even PCA. So which tells me that, well, I am converging almost in the same way of using the original space versus versus the reduced space in this case. Well, it's only at 85% that I'm seeing that 1% of accuracy has been dropped over here, which means that if I'm using only 81 features, of course, these are not the original features, but the new PCA features, that I'm seeing only 1% accuracy drops, which is honestly insignificant in this case. Okay, so what's this slide just shows us what are the applications of PCA. Of course, we can use it for compression. And here, yeah, and needless to say that it reduces the memory and the disk needed to store the data. There is a significant speed up in terms of the learning algorithm. Just like I said earlier, we have a tendency to converge faster because we're training with less columns or less features. So the conversions will be faster in this case. Uh, it's always mostly used in the literature. If you look at the papers in Google Scholar and say that, or pick up any paper which uses a 2D or 3D visualization of the data set, it's going to be highly probable that they are using PCA or a Tisney method in using k is equal to 2 or k is equal to 3 in order to do their exploratory data analysis on the data and trying to visualize it before trying to apply any supervised or unsupervised learning method on it. A bad use of PCA is going to be to train the model faster and try to avoid overfitting, right? It should not be used for reducing the feature space and for feature selection. It's not a feature selection method, right? It is a data compression method, right? So I am compressing the data for the sake of reducing memory need and for the sake of exploratory data analysis, but not for the learning. Do not use it for the modeling process or for reducing the space before training your classifier, for example. Another dimensionality reduction technique that we study is the Fourier transform. So the key idea behind Fourier transform is that any time series or signal or image can be approximated, and that using a sum of sine or cosine functions. So essentially, even if a signal looks very complex in the time domain, it can still be represented using only a small number of frequency components. So the idea is that after applying the Fourier transform, we no longer store the original signal in the time domain, but instead we just record the frequency domain transformation of that particular signal. So in the frequency domain, each component is represented using three informations. Typically, that's the first one, as the name suggests, is the frequency, right? So it tells us how fast is the sine or the sinusoid oscillates, right? So does it go very fast, or the oscillation is on a lower or on the slower end? So that's the frequency. The second one is the amplitude, which is the Y, right? So it tells us how strong that frequency component is. And finally, the phase, because when we talk about sinusoidal curves, of course, we can start it from different points, right? I can start it from the peak, or from the valley, or from the intersection point between the x-axis where we have zero over here. So that tells us where the sinusoid is aligned in terms of time. So once we have these representations, dimensionality reduction becomes pretty straightforward, because I just need to record these three components and how many sinusoid functions are being used in this case. In fact, many real-world signals contains high-frequency components, but a very small amplitude. So these often are just considered to be noise, or just fine details that are not very important. So essentially, the idea is that we would like to keep only the high remove the high frequency signals, right? So the very small ones that you could see over here in the slides, right? So these are typically the ones which are embodying only the noise, or this very fine details that are typically not catching the eyes when you look at a particular image, or a bit, or some time series. I would like to keep as much the high level details that are obvious when I see the object in 2D, or in a time series formats, which are the ones which are having low frequency components, the very first sine curve or cosine curve in this case. So by doing this, a complex signal can easily be stored using very much far fewer parameters, because we can throw away the original time series, which is, let's say in this case, 100 dimension, and I can keep only three informations per sine curve. I can keep what's the frequency, what's the amplitude, and what's the phase of every single signal that I chose that I choose to use for my dimensionality reduction. Now let's say that I chose my three first signals, right, or three first sinusoid curve in that case. For every sinusoid curve, I will keep these three different parameters: frequency, amplitude, and phase, and then I can combine them back together in order to form my approximation of that original signal. You could see here in this figure on the top right that my Fourier approximation, which is the aggregation of all these the sinusoid the curve that we have in the slide, is the one dotted line over here, right? And you could see clearly that, well, it is it is an addition of the blue with the red, and the deep blue sinusoidal curve that we have here. So y3, y5, and the first y in this case. My original signal is also shown as this in this particular slides over here. The square function is the one which is being approximated in this case, which is this blue line over here. Uh, of course, my approximation looks a little bit like a sine curve, because that's the base function that I used, but this is quite a good approximation in the sense that the dotted line grasps the big picture, or the general shape of my square function, and my starred line in this case. Okay, so in this slide over here, we're showing that we're moving from the time domain, which is my original time series domain, which is the squared function blue line over here in t, which is my x-axis, and we're moving towards the frequency domain over here because our frequencies are in terms of phase, amplitude, and frequencies in the sinusoidal domain. So we're no longer talking in terms of time, but rather in terms of frequency in this case. And that's the whole idea behind Fourier transform. Okay, so now the second one is a wavelet transform. It is the same idea as a Fourier transform. It's still using a base function in order to represent an approximation of the signal. And why this is important is because, well, while the Fourier transform is powerful, it has one major limitation. So the main limitation is that Fourier tells us what frequencies exist, but it does not really tell us when do they occur, right? So in other words, Fourier answers the question like what frequencies exist in the signal, right? So we have like maybe this frequency, that frequency, and that one, but it does not tell me by naked eye, right? If you look at the y1, y3, and y5, you cannot say that okay, there is some patterns along which time steps of my original signal over here. So where do these frequencies appear in the time and space is the question that wavelet transform is answering for us in this case. So the wavelets improve upon the Fourier transforms, and it does so by capturing both the frequency as well as the time localization in the x-axis. We're going to see that in a few seconds. Okay, so let me start the question first of what is a wavelet. So wavelet in this case is a very small wave. Like you see here, Debauche's the quafflet, the Haar, and the Simlet wavelet are a very small wave. If you take the mean of this wavelet is going, mean of all the values, the wavelet is going to be zero, and it's usually living in a very short time, right? So these are not, it's a very small segment of in time that where those wavelets are living. So because wavelets are localized, they allow us to capture local patterns in the data. So this makes them quite useful for signals where the patterns changes over time, such as time series, images, or even sensor data. So okay, so in this case over here, you could clearly see that this is the JPEG compression, right? So in fact, JPEG 2000, not the regular commercial JPEG compression that you see and that you use every day. It uses wavelet transform. JPEG 2000, in fact, is a more expensive version of JPEG. It is more computationally powerful and also demanding. That's why this it's not the go-to JPEG that you're typically using on every day, but it is also it has a high localization capability because it's using wavelet behind its practice over here. So, uh, so wavelet, you could see here an example of how the wavelet works, which is the x prime over here, which is an approximation of the x. You could clearly see that it's using here, using the Haar wavelet, which is the second or the third shape over here. The third shape or the Haar wavelets are the most common and popular wavelet that are being used everywhere using wavelet transform. So the wavelet-based dimensionality reduction follows a quite a straightforward process. Well, first, it transformed the signal into a wavelet coefficient, right? So you could see here the wavelet coefficient Haar0, Haar1, Haar2, Haar3, all the way to Haar7 in this case. And it only keeps the largest coefficients, which corresponds to the most important patterns, and it discards the rest. So the highest coefficients are the ones that are shown, let's say, at the very beginning. Haar0, Haar1, and Haar2 are the most important one. And of course, you could see that Haar7 captures a smaller space and a smaller, and therefore it has a lower coefficient. In general, it can easily be discarded in this case. So So the reason why we say that wavelet transforms are localized, they have the addition capability to show us where the patterns exist in our data set, is that if you look at the HARs, right, or the wavelet the transform coefficients over here from 0 to 4, you could clearly see that HAR3 is embodying this particular segment, right? If I were to draw here, you could clearly see that if I am interested to know what happened in the segment of from 0 until, let's say, 25% of the length of the data set, then I can easily do so by looking at HAR3 and in this case HAR2 as well as HAR1 over here, right? So these are highly localized over here. So if there was some pattern going on, I could clearly see it on directly through the wavelet transforms over here. While if you look back for the case of the Fourier transform, you won't see much, right? You will see just a sine curve over here, nothing going on. It's just a frequent sine curve without telling me much about what happened in that particular segment in time over here. So it is a localized wavelets are localized. You can easily guess what happened in each segment of the data set of the X over here without having to even merge them and aggregate those HARs together to reproduce my X prime in this case. So because of that particular advantage, then we can clearly see what are the patterns at the X-axis and where do they occur without aggregation. So in this case, it allows us also to significantly reduce dimensionality as well, just like Fourier transform, because it is still, we are still getting rid of all the high high dimensional or the HAR6, HAR7, etc. over here, since they are embodying the smaller details. It has one main challenge here or constraint, is that the data vector must have a length of 2 to the power something. If it's not 2 to the power something, then what happens is that usually the method has fails because it approximates the left hand side of the signal way better than the right hand side. You can easily try to pad your data set, right? Add some padding, zero padding to your data set in order to make it of 2 to the power n, to the power sum of n in this case, in order to be able to have a good approximation of your original signal x in this case. Okay, so when using wavelets, we are essentially asking the question of, is there a pattern like this particular wavelet at this scale, at this location, and at this particular scale, right? And this location, which is half of the signal for HAR1. And how strong is it? Sorry. So this brings us to three key components of wavelet representation, right? So typically, well, as we said earlier, for Fourier transform, we keep the frequency, the phase, as well as the amplitude as the attributes that we keep for retrieving our Fourier transforms. Now that we know what are those wavelets that we're going to use, then we keep in mind three different variables as well. The first one is the scale, uh, and the scale controls two things: the frequency as well as the resolution. So a small scale means that a large or a large scale, it corresponds to a low frequency and coarse resolution, while on the other hand, a small scale, or it corresponds to a high frequency and finer details, right? So which are happening at the very bottom over here of HAR6 and HAR7 in this case. So that's the first one. Scale is the first parameter. The second one is the shift. And the shift, it controls the location, right? So it slides the wavelet along the signal, and it captures where something is happening in time or space. So that's my second parameter that I keep record of when I am making my wavelet transform approximation here. And the last one and the final one is the coefficient value. So the coefficient tells us how strong that feature is at a particular scale and location. So uh, the strength of the feature is measured by the coefficient value in that case. For every single Haar wavelet that we have over here, we keep those three parameters, just like we did for Fourier transform. Now, in data mining applications, typically the Haar wavelets are commonly used because they are simple, efficient, and quite effective, and they have been quietly used in multiple applications. In this particular example that I have in the slide, I believe they are using the Simlat wavelet over here, and feel free to go to this particular resource to read more about that. Okay, so again, in the midterm exam and the quizzes and assignments, I will not ask you to implement Fourier transform nor the wavelet transform, but I'm expecting you as to know what are their limitations and how do they work in general, as far as what are the parameters that we need to that we need to keep record of, and what are the limitations of both. Right, so we said the limitation of wavelet is 2 to the power n. The limitation of Fourier is the fact that we don't really know. It is not a localized, but it is rather a general method which does not tell us where a particular pattern is happening unless we reconstruct the signal into its approximation x prime over here. Okay, so we already talked about what's a wavelet, and we said that this is a small signal. For example, a sine wave is not a wavelet because it's a long signal over here. Although it does have an average value of 0. If you take the average of all those values over here, they will cancel out each other. But it lives in a longer interval. A wavelet, on the other hand, will live only in a short interval, not the whole interval in the x-axis in this case. Okay, so now the question is sine or cosine wavelets, and the answer is no, they are not wavelets. A wavelet is typically the one which is shown in this slide in the third line. It lives only in about 30% of the time series in this case, and it has an average of 0. Okay, so now we're moving to talk about data reduction from a perspective of dimensionality reduction of feature subset selection. So all what we have been talking about so far are data or dimensionality reduction using some data for the purpose of data compression, right? So now feature selection is quite a different thing that we typically do before modeling, and this is also for the sake of reducing the size of the data set and having a more powerful model by reducing redundancy in the features, and also speeding up the process of the learning. So, uh, so typically, we talk about if you were to find all the possible features that exist in my data set, right? So, if I have p attributes or p column, the problem is very hard. I need, in fact, 2 to the power p possible selections, which can get a very large number of possible comparisons when we're talking about thousands of features in our column levels. So it's not very much easy over here. There are typically two ways to go about it. The very one is the easy way and the straightforward way, which is known as a filter method. So the way it works is that, well, I have a feature space, and for every single column, I will find the correlation of that column with my y values, or which is my target variable, and I will pick up the columns which have the highest correlations. Right? These are known as a filter method. These are independent methods from each other in the sense that every column is being separately evaluated without the knowledge of the other features in the data set. The second family of methods are wrapper methods, and in this case, I am using a model itself for the evaluation process, in the sense that I have a feature space. I will remove one feature at a time, and I can say I can measure what's the impact of removing that feature on the learning process. If I see that, well, there is no impact, then probably it's a clue for me that this feature is not very much interesting or very much powerful here. If I see, on the other hand, that removing a feature will significantly lower the accuracy of my model, then I can say that, well, this is a good feature. I should probably select it and avoid removing it in the latter process. So data reduction here is an example of the very first family of methods, which are the filter methods. So using filter methods, I can use some measures like the mutual information or the entropy. Typically, some papers are using Pearson's correlation scores in order to find what's the importance of that feature. And here is an example of a toy data set which has glucose, BMI, age, pregnancy, diabetes, pedigree, function, blood pressure, triceps, serum, and insulin. And you could see the importance of those data sets using one of those measures or metrics that I talked about. It could either also be the variance level if you wish, right? So I can pick up I can say that my importance or my feature importance is in terms of variance. The most variant, the feature with the highest variance is the most important one in my data set. Well, in this case, it looks like BMI and age do have similar importance. Glucose is the highest importance in this data set with respect to the target variable. In this case, a target variable could be the class of the patient, right? Either the patient is sick or is a perfectly healthy patient in this case. So we can select the top K features and drop the rest of the features over here, which have the lower importance in this case. Now, my second question, and here, hear me out because this is a very important one. I might ask you about it. Is that here? So, what if I have two features that have exactly the same importance, right? Uh, which one should I take? Because they are, let's say they are correlated, right? So age and BMI in this case are equally important. So I can keep them. But what if they are also highly correlated, right? So if two features are highly correlated, which means it means that they are giving me the same amount of information, or they are contributing with the same amount of information. I don't need both of them. Only one of them is enough. For example, date of birth and age are highly correlated. In fact, they give me the same exact information here. For the weather as well as the season might be correlated, might be some correlated variables as well. So typically, how now my answer is I will always go with the variable with the highest variance. So if two features have the same are highly correlated, I will choose the one with the highest variance because, as I said earlier, as data miners, variance is our best friend. We always want to have high variance because that's also the same concept that is being used in PCA. A variance will allow me to have data scattered across a bigger space and therefore a larger space where the model can freely move and find a function in order to split the data set in that high dimensional space. So that's what I mean by a high variance in this case. Okay, now which leads me to the next slide over here. The first slide in slide 51 over here, we're talking about the wrapper about the filter method. Now we're talking about the wrapper method. The wrapper method is when I'm using a model that will tell me that will do the feature subset selection for me. There are two ways. Both of them are more or less the same thing, but one of them is just starting from bottom up. The other one is top down. So backward feature elimination is when I keep one attribute at a time, which means that so if I just share my whiteboard for a second and try to explain this to you over here. So let's say that I have a feature space, right? And I have many attributes, right? So let's call them features, right? So F1, F2, all the way to FM, right? And again, I have multiple tuples or multiple objects over here, and let's call them O1, or X, since we use X for the PCA explanation over here. So X1 all the way to Xn. So now let's say that I want to use a wrapper method using a backward method. So the way it works is that, well, I will train and in here I have my target variable, of course, since it's a classification. So I have my Y here. The Y could be easily like, let's say, a healthy patient versus a sick patient in this case, right? Let's say for the binary case of healthy or sick in this case. Now, the way the backward feature selection works is that I will train my model with all the features without F1, and I will record what's the accuracy. Let's say that the accuracy is 90%. Okay, great. Now I will do the same thing, but now I will train with everything except from F2, right? Now, okay, so now the accuracy dropped to 70%. Uh-oh, what this tells me? This probably tells me that F2 is a good feature in this case. Okay, now I'll do the same exact thing for all the features in my dataset until I finish all the M features that I have. Now the third feature will give me, let's say, 99% accuracy, which tells me 99% is probably, well, what this tells me is that I can easily discard F3 over here, the feature number 3 over here. The accuracy is almost perfect without F3 in this case. Right. All right. So now if you plot this into just a bar plot over here, and which is here in this case accuracy of the model, and this and accuracy, and these are the features that I have, and you can easily rank them by the highest to the lowest over here. You could see that, well, in F3, this is F3, right? Without F3, training everything, the model with all the features without F3. This is training the features, all the features without F1, and this is training all the features without F2 in this case. We can easily get rid of F1 and F3 over here because the model is doing 90% and 99%. So I can easily reach a 99% accuracy by removing F3 from my feature matrix or my feature space over here. So this is what a wrapper method is. I am using a model. That model could be easily a random forest or any downstream machine learning models, SVM, a random forest, the decision tree, or anything that you like, in order to give us a sense about what is the impacts of removing one feature from the matrix. Okay, so now that I removed F3 from my features space over here, I can do the same thing with the remaining features from F1 all the way to Fn, F1 and F2. Let's say that I had only 3 features in my matrix over here for the sake of easiness over in this case. So now I'll train my new model again using only F2 and only F1 and record what is their accuracies. If I see that, well, with only F2 the accuracy has dropped significantly, then F2 then I must keep F2. In fact F2 it should be a selected feature over here. And the same thing for F1. If I see that F1 is insignificant like F3, then I can easily remove that from my feature space. So feature selection allows us to, number one, make our feature space way smaller, and so the learning process will be faster, and hopefully we'll have even higher accuracy at the end of the process as a byproduct of this feature selection here. All right, so let's go back to the slides over here. So backward feature elimination is what we just discussed. Forward feature selection is the inverse process, where we train the model at one feature at a time, right? So I'll train the model only using F1 and see what's the accuracy. Only F2, see what's the accuracy, and then I'll pick only the top K features which have the highest accuracies individually when trained on that particular model. Okay, so this is the way to do feature selection when relatively we have a smaller feature space, especially when we are talking about the vector data set here when not a lot of features are being involved. But again, remember that this process is an independent process, right? So if you want a dependent feature selection method, then you might even have a look at more smarter and sophisticated methods like minimum redundancy, maximum relevance, which is known as the MRMR. You can read more about it. And it also uses the concept of variance levels, just like PCA. Okay, so feature creation is the inverse of what we've been talking about. So I'm creating new features, hopefully aggregating some of them in order to get rid of many features, right? So that's what a feature creation is in this case. An attribute construction such as data combining features together and creating something with multiple features might be helpful for reducing the size of the data set at the horizontal level and reducing the number of columns as well. Okay, so up to this point, we have focused almost entirely on the first part, which is highlighted here, and this is the dimensionality reduction. So we discussed up to now several techniques such as handling missing values, the low variance filtering, high correlation, and the wavelet transform. So all of these methods share one goal, and this is reducing the number of attributes or features. Um, and we would like to keep as much information as possible. So, but here, the dimensionality reduction is only one side of the data reduction. In fact, starting from this slide, we will shift our focus to another major category, which is also called numerosity reduction. So, where instead of reducing the number of features, we would like to reduce the number of data points or the size of the data set itself. So think of this as a transition from everything above is the line is we already covered. Now we will move to some kind of new idea of data reduction here. Okay, so numerosity reduction is the very first method for reducing the volume of the data. And the idea is that we would like to replace the original data set with a much smaller representation. And in fact, there are two main approaches here. So we have the parametric approach and the non-parametric one. So in the parametric approaches of data of numerosity reduction, we assume that the data follows some kind of model. For example, here this is a line, a linear, it could be a linear regression in this case. So we can estimate the parameter of that particular linear regression as an example of that or any type of other model. And then we can discard all those scatter points that we have over here by only keeping the parameters of that line. Uh, so you can imagine that will save us a lot of storage because we if you of course if it's a linear regression, I just need to know what's the slope of the line and what's the intercept, which is a and m, and I can discard all those scatter blue points that you can see over here. I don't need them because I just approximated the whole data, which was taking me probably a matrix of 100 by 2 dimensional. In this case, I just approximated using two parameters in this case. It's parametric because I just need to remember the parameters of the model that I just approximated it with. Okay, now the non-parametric approach, on the other hand, it makes no assumption about the data, right? Just like we did earlier. It does not assume that it follows some kind of model here, but instead it just summarizes the data using some kind of representation. For example, here we're using either a histogram or a cluster, etc. So we're not really having some models, parameters that we're keeping in mind, but we're using the underlying distribution or the clustering of the data in order to approximate it in case I need to retrieve the data back into for modeling purposes. Okay, so this slide just gives us another a broad overview of the most common techniques used for numerosity reduction. So on the parametric side, we have simple linear regression, like I talked about in the previous slide. multiple linear regression, log linear models. So these methods fits some mathematical function for the data, and it only keeps the learned parameter, like I mentioned. And on the right hand side, in the blue ellipses here, we have the non-parametric side where we have histograms, clustering, sampling, data cubes. So these approaches just summarizes the data, or it tries to group them instead of fitting it into a particular equation. Um, so, um, so moving on to the next slide here is the very first method over here. So this is a regression, right? So it's a simple regression. You can easily see that or guess that using this particular equation here. So B0 is the intercept, B1 is the slope. You could see that the data follows a straight linear line. Here, if I know B0 and B1, then this is my very easy parametric approach of trying to estimate the data by randomly creating the data set in case I need so by if I know this line. So let's say that my data set is made of 10 or 15 tuples or even 100 tuples in if we're being realistic about real data set. Now, I don't want to remember the whole data set, but I can approximate it when the modeling for when the modeling is comes, then I can generate randomly 100 points using this y equation here, or my linear regression line in this case. So once we estimate these parameters, we no longer need the full data, right? Or the full data set. The model can become the compressed representation of the data set in this case. Okay, now the second slide over here, this is still a regression slide, but as you might guess, this is a multiple linear regression, and we just extend the previous idea to multiple predictors and using the same equation, but with more that with multiple variables in this case. So when the relationship are more complex, we might need these kinds of non-linear regression line over here. So it's not really a linear model that we're talking about, where the relationship between x and y is no longer just a straight line here. So from a data reduction perspective, all these methods share the same idea, right? So we're just replacing a large data set with a small set of parameters that can summarize the underlying trend in my data set here. Histogram analysis is another just classic approach for non-parametric numerosity reduction technique. So instead of storing every individual data points that we have or every single tuple, we can divide the data into different buckets, right? And these are also called the bins of my histogram. And for each bucket, we only keep some representative values, such as what's the average, the minimum, or the maximum of that bucket. And discard the original values. So now, if you look at the very much the bottommost histogram over here, I can easily remember only what's the average inside of this bucket over here, right? So for every single bucket that I have, which are 5 buckets, I'll just remember what's the average value inside of each bucket in this case, right? Which gives me only I will at the end of the process I will remember only 5 value per bucket, which is extremely cost savvy in terms of data, in terms of memory. If you were to remember only those values versus the whole data set, so it's a really great approximation in this case. Okay, now the last slide that I will cover today is the difference between different types of histograms. And here we're just visually comparing equal width versus equal frequency histograms. So in equal width histograms, each bins is really spanning the same value range. You could see minus, so minus to 10 and 10 to 20 and 20 further over here. So this is my equal width histogram, but it can perform poorly when the data distribution is kind of highly skewed, right? So for highly skewed distribution, we might want to use something else. So in equal frequency histogram, in this case, each bin contains the same number of data points. So this approach is better for skewed data, but it might produce bins with very different width as well, right? So different width might be kind of misleading as well when you're reading those histograms and trying to assume what's the underlying data distribution. Like we said earlier, is it a gamma distribution, or is it a normal distribution, or so? So neither approach is universally better, but the choice depends on the data distribution and the application. So I think the important takeaway here is that histograms allows us to reduce the data size, and it also prefers the overall distributional shape. So I think I'll stop here. You've have a lot of content already, and I will let you have fun with the series, with the practice series. If you have any question, I will welcome them in the beginning of next class. Thank you very much.